Okay, welcome to the class. Today we're going to have a look at the second lesson of chapter 4. Today's topics are gravitational potential energy and the law of conservation of energy. Okay, first of all, let's have a look at gravitational potential energy. The extreme sport of heli skiing starts with a helicopter ride to the top of the remote mountain. A skier like the one shown here in this figure then jumps out of the helicopter onto the steep slopes. How do you know that the skier is in figure 1 has energy before jumping from the helicopter? How can this energy be transformed into another form? In this section, we'll learn the answers to these questions. So you can sense that the skier shown here in this figure has energy because of his or her height above the ground. The force of gravity will do work on the skier as soon as she steps out of the helicopter. As she falls, then skis down the mountain, his or her kinetic energy will increase. Her or his height above the ground means that he or she has a potential to pick up kinetic energy from the force of gravity. This potential to increase kinetic energy is a form of stored energy. The stored energy that an object has that can be released into another form of energy is called potential energy. Many forms of potential energy exist. A long jumper posed to jump has potential energy stored in his muscles, and the flexed muscles have stored biochemical energy that is released as the jumper springs into the air. A stretched elastic band also has elastic potential energy. When you let an elastic band go, the potential energy becomes kinetic energy. Kinetic energy and potential energy have a close relationship, and one form can transform into the other as work is done on or by an object. The sum of the kinetic energy and potential energy of an object is called the mechanical energy of the object. We will learn more about the properties of mechanical energy in section 4.5. In this section, we'll focus on the potential energy only, and specifically the potential energy an object has due to gravity. Okay, so now let's have a look at the concept of gravitational potential energy. An object near Earth's surface has a potential energy that depends on the object mass, m, and height, h. The gravitational energy, which is often denoted by Eg, is stored energy as a result of gravitational force between the object and Earth. Although we will often speak of gravitational potential energy of an object, note that Eg is actually a property of the object and Earth together. Potential energy is always a property of a system of objects, as we'll discuss in section 4.5. So analyzing gravitational and potential energy mathematically can help clarify how to apply it when solving problems. So here, suppose a walker lifts a crate onto the back of a pickup truck, as shown here in figure 2. Let delta y be the change in the elevation of the crate. The force the walker applies to the crate to raise it is in the same direction as the crate's displacement. The work done on the crate by the force then can be given by this formula, W equals F times delta D times cosine theta, right? So in this case, theta equals 0, so We know W equals mg delta y. Also note that we replace delta D with delta Y because we often use Y to represent vertical displacements. When the bottom of the crate reaches the height of the truck's bed, the crate has gravitational potential energy relative to the ground. Suppose a walker decides instead to place crates on top of each other. You could then describe a crate's gravitational potential energy relative to the ground, or describe its gravitational potential energy relative to the truck bed. Since gravitational potential energy depends on position relative to an object, it is relative quantity. It is a relative quantity. Its value depends on the height of the object above some point of reference that you choose. You can choose the level that is most convenient for solving any given problem. The work done to increase the elevation of an object relates to the change in the elevation instead of a specific height, which means delta Eg equals mg delta y, which is illustrated here. So when delta Eg is the change in gravitational potential energy, m is the mass, g is the gravitational acceleration, and delta y is the vertical component of the displacement. This equation for gravitational potential energy presents a few important points to consider. First, the equation determines the change in gravitational potential energy for a given change in elevation. It does not assign a fixed value of potential energy to a given elevation, but only the difference in potential energy between different elevations, delta y. You can freely choose a reference point to act as a zero gravitational potential elevation. When solving a problem, choose elevation that is most convenient for that problem. For Earth's surface is often a convenient choice, but it is not the only choice, or necessarily the best choice. Choose a reference point that will result in the easiest calculations. Often, choosing the surface of Earth for this point is most convenient because gravitational potential energy will then be either zero or positive. Second, delta y does not depend on any changes in horizontal position or on the path the object took to reach its new height. When the object increases its height, delta y is positive. When the object falls to a lower height, delta y is negative. Finally, we'll read in the next chapter that the acceleration due to gravity actually varies slightly by height above Earth's surface. The equation above is only accurate when the change in height is small enough that we can ignore the change in g. An object thrown upward will begin with kinetic energy, but the amount of kinetic energy decreases as the object slows down because of the gravitational force. At the same time, the object gains potential energy as its height increases. Whenever an object falls, the force of gravity will do work on the object, giving it kinetic energy according to the work energy theorem. At the same time, it loses gravitational potential energy. Suppose that we hold a physics book above our desk. If we drop the book, its initial velocity is zero, right? But it has gravitational potential energy relative to the desktop. As it falls, the force of gravity does work on the book and converts its gravitational potential energy to kinetic energy. Before it hits the desktop, all of its initial potential energy relative to the desktop has converted into kinetic energy. As the book strikes the desktop, kinetic energy is converted into sound energy, thermal energy, and other forms of energy. Also, you should be careful with the units of gravitational potential energy. Gravitational potential energy and kinetic energy are different manifestations of the same quantity, which is energy. They both have the same units, joules, and both are scalar quantities. In the equations below, we can see how to calculate the units of gravitational potential energy. We have delta Eg equals mg delta y, right? The units of m are kilograms. The units of g are meters per second squared. The units of delta y are meters. So putting these facts together gives us the units for gravitational potential energy is joules. Similar to kinetic energy, no direction is associated with gravitational potential energy. So next, let's have a look at a tutorial which examines how to use gravitational potential energy in problems involving rising and falling objects. Okay, so now let's consider tutorial 1, applications involving gravitational potential energy. Okay, so sample problem 1, calculating gravitational potential energy. A hiker stands near the edge of a cliff and accidentally drops a rock of mass 1.2 kilograms to the ground at the base of the cliff, 28 meters below, which is shown here in this figure. Can you calculate the potential energy of the rock relative to the ground just before the hiker drops it? Okay, I'll give you 5 minutes to have a look at this problem. Well, which is actually pretty straightforward, right? All right, so in this problem, we are given the following information. The mass of the rock is 1.2 kilograms, and the acceleration due to gravity is 9.8 meters per square second by default. This is a value of this acceleration near the ground of the Earth, right? And if we choose the ground as a reference point, be careful with this because before you calculate any potential energy, you need to choose a reference point first. Also, the positive direction of the y-axis. So if we specify the ground is the reference point, so we know delta y is 28 meters, right? So use the gravitational potential energy, delta Eg equals mg delta y. Then put all the values in. We have the potential energy delta Eg is approximately 3.3 times 10 raised to the power of 2 joules. So the rock's potential energy just before the hiker dropped it is 3.3 times 10 raised to the power of 2 joules. Okay, any questions? If not, let's have a look at the next one. A weightlifter raises a loaded barbell 2.2 meters. The lift increases the gravitational potential energy of the barbell by 490 joules. Determine the mass of the loaded barbell. Okay, I'll give you 3 minutes to consider this question by yourself. Then we'll have a look at the solution together. All right, next one. Let's have a look at the solution here. Okay, so in this question, we are given the following information. Delta y is 2.2 meters. Gravitational acceleration due to gravity is 9.8 meters per square second. And potential energy, gravitational potential energy, delta Eg is 490 joules. And we want the mass of the barbell, m. So we can rearrange the gravitational potential energy equation to solve for m. Because we know delta Eg equals mg delta y, so we can divide both sides of the equation by g delta y. That gives us m equals delta Eg over g delta y. And then put all the values in, we can find the mass of the barbell is approximately 23 kilograms. All right, do you have any questions? Okay, so if you have no questions, let's have a look at another sample problem. And this problem shows us the gravitational potential energy and the work energy theorem. Okay, so we have a physics book textbook, which is 3.6 centimeters thick and has a mass of 1.6 kilograms. A student stacks 10 of the books in a single pile on a table. Each book starts from table level before the student lifts it to the top of the stack. So there are 3 questions. A, calculate the gravitational potential energy of the stack of books with respect to the table. Then determine the total work done by the student to make the stack of books. C, calculate the work done by the student to move the books from the stack and set each on the desk. Okay, so I'll give you 5 minutes to consider this question by yourself, then we'll have a look at the solution together. You can start now. All right, now let's have a look at the solution together. Okay. So we are given the following information. The height of each book is 3.6 centimeters, which is 0.036 meters, and the number of books is 10, right? So in question A, each book has a separate gravitational potential energy. Since the first book does not move, no energy is expended. The second book is lifted 3.6 centimeters. The third is lifted 2 points this value, right? And so on. The gravitational potential energy of the stack is the sum of the gravitational potential energies of all the individual books. In question B, since the work and energy use the same units, W is equal to the gravitational potential energy of the stack. And in question 3, the work done to move the books from the stack should be equal to the is equal in magnitude to W, but opposite in sign. Okay, so delta EG is mg delta y, which is 1.6 kilograms times 9.8 meters per square second times the sum of the numbers here. And also note that we can put the common factor 0.036 in front, and which left is a arithmetic sequence. So there is a shortcut to calculate the sum of the arithmetic sequence, right? Which is the first term plus the last term times number of terms over 2. Okay, so the final result is approximately 25 joules. And the work done is also 25 joules. So we can make the final statement like this. First, the potential energy of the stack relative to the table is 25 joules. B, the work done by the student to create the stack is also 25 joules. C, the work done to move the books from the stack is negative 25 joules. Okay, do you have any questions? If not, let's take a short break. Please return before 15 past 10, and we'll have a look at the second part of this lesson, which is about the law of conservation of energy. Okay, you can take the break now. All right, welcome back to the class. So next, let's have a look at the second part of this lesson. Section 4.5, the law of conservation of energy. Imagine the thrill of the riders as the roller coaster in this figure moves up and around the loops, over and over again. What do riders feel as they near the top of each loop? What do they feel as they move down toward the ground again? What makes them feel these sensations? In this part of this lesson, you will explore some of the physics related to roller coasters, sports activities, and other movements we experience every day. We will learn about the exchange between gravitational potential energy and kinetic energy that occurs when objects move. Okay, so first of all, let's have a look at the energy transformation theory. As a diver climbs a steps to the top of diving platform, her gravitational potential energy increases relative to the water surface. As she dives towards the water, her gravitational potential energy decreases. At the same time, her kinetic energy increases as her downward speed builds. When she hits the water, her gravitational potential energy relative to the water surface is 0, and her kinetic energy is at a maximum. Although her gravitational potential energy decreases, the energy does not just disappear. As her kinetic energy increases, it too does not just appear from nowhere. The potential energy transforms into kinetic energy as the diver falls. Energy is neither created nor destroyed. It simply changes form. In fact, the total mechanical energy, the sum of kinetic and potential energy, remains constant. This important law of nature is called the law of conservation of energy, which states that energy is neither created nor destroyed. It can only change form. The law of conservation of energy is one of the fundamental principles of physics. To take into account apparent energy losses due to the friction and other effects, the statement above will be refined in the next section. We will use the law of conservation of energy as a tool for solving many problems. The total mechanical energy of a moving roller coaster car is the same at every point. That is, the sum of the gravitational energy and the kinetic energy remains constant. The total initial energy, ETI, equals the total final energy, ETF. For situations involving only gravitational potential energy and kinetic energy, the equation can be written as EGI plus EKI. That means the sum of the gravitational potential energy and the kinetic energy in the initial state equals EGF plus EKF, which means the sum of the gravitational potential energy and the kinetic energy in the final state. Knowing the energy of a roller coaster car at the start of the ride enables you to determine the gravitational potential energy and kinetic energy at any other points. The following tutorial examines how to use conservation of energy to solve problems involving motion. Okay, so now let's have a look at a tutorial here. Applying the law of conservation of energy. Well, actually, we have done this problem before, right? So this time we'll use another different method to solve this kind of problem. A 67-kilogram snowboarder starts at the top of an icy or frictionless hill of a vertical height 22 meters with an initial speed of 15 meters per second. A. Calculate the snowboarder's mechanical energy at the top of the hill. B. Calculate the snowboarder's speed at the midway point and at the bottom of the hill. Then describe the energy transformation that occurs as the snowboarder moves down the hill. Okay, I'll give you 5 minutes to consider this question by yourself. Then we'll have a look at the solution together. All right, have we finished? Okay, let's have a look at the solution here. Okay, question A, we are given the following information. Mass of the snowboarder is 67 kilograms. Delta Y is 22 meters if we select the ground. The lowest point of the ground as our reference point. The initial speed of the snowboarder is 15 meters per second. And first, we want to find the snowboarder's mechanical energy at the top of the hill. Okay, so choose the bottom of the hill as h equals 0 reference point, then set the gravitational point potential energy at the top of the hill equal to this amount. Delta Eg is mg delta y, right? And the gravitational potential energy is, the kinetic energy is 1/2 of mv squared. So the mechanical energy ET equals Eg plus Ek. And let's put all the values in. Delta Eg is 1.444 times 10 raised to the power of 4 joules. And kinetic energy is 1/2 of 67 times 15 squared, which is about 7.537 times 10 raised to the power of 3 joules. So the total mechanical energy at the top of the hill is then approximately 2.198 times 10 raised to the power 4 joules. So we can make the following statement. The snowboarder's mechanical energy at the top of the hill relative to the bottom of the hill is approximately 2.2 times 10 raised to the power 4 joules. Okay, next let's consider the question B here. We can use the law of conservation of energy to relate the initial and final energies. EGI plus EKI equals EGF plus EKF. In each case, delta EG is mg delta y, and EK equals 1/2 of mv squared. So the total mechanical energy at the midpoint and the bottom of the hill will equal the total energy at the top of the hill, which we have already got, right? Which is 2.2 times 10 raised to the power 4 joules. Since the hill bottom is the h equals 0 reference point, the gravitational potential energy at the midpoint is Eg equals mg delta y, which delta y equals 11 meters. So Eg is 7.223 times 10 cube joules. And then the kinetic energy is Ek equals Et minus Eg, which is 1.476 times 10 raised to the power 4 joules. Then we can calculate the speed at the midpoint. According to the formula, Ek midpoint equals 1/2 times mv squared. Then we can have v equals square root of 2.2 times 1.476 times 10 raised to the power of 4 joules over 67 kilograms, which is about 21 meters per second. And actually, we can use the similar method to calculate the speed at the bottom of the hill, right? And the speed of the snowboarder at the bottom of the hill is 26 meters per second. So halfway down the hill, the snowboarder's speed is 21 meters per second. Our speed at the bottom of the hill is approximately 26 meters per second. And in question C, we can state that as the snowboarder moves down the hill, her height above the reference point decreases, reducing her gravitational potential energy. Her speed, however, increases. The gravitational potential energy continuously transforms into kinetic energy until she reaches the bottom. Okay, have a look at this question. Do you have any questions to ask? All right, if you don't have any questions, let's have a look at another sample problem. Determining maximum height and speed using the law of conservation of energy. Okay, so this figure shows a 0.45 kilograms bullfrog jumping with an initial speed of 6.2 meters per second at an angle of 49 degrees above the horizontal. Assumes that energy losses due to air resistance are negligible and can be ignored. First, can you calculate the maximum height of the bullfrog's jump? And then calculate the components of the bullfrog's velocity when it first reaches a height of 0.8. Okay, I'll give you 10 minutes to consider this problem by yourself. Then we'll have a look at the solution together. All right, have you finished? Okay, let's have a look at the problem in detail. Okay, in question A, we are given the following information. Mass of the bullfrog is 0.45 kilograms. HI is 0. VI is 6.2 meters per second, and theta equals 49 degrees, as shown here in the figure on top right. And we want to find delta Y here. Okay, the bullfrog's velocity in the horizontal direction does not change because no horizontal force acts on the frog, right? Since the change in the horizontal velocity is 0, it has no effect on the change in kinetic energy of the bullfrog. The kinetic energy from the bullfrog's vertical component of velocity decreases and transforms into gravitational potential energy. You can solve the problem by comparing just the vertical parts of the kinetic energy and the gravitational potential energy. Okay, so the initial speed is 6.2 meters per second. The initial horizontal velocity is then Vx equals Vi times cosine theta, which is approximately 4.07 meters per second. At the high point of the jump, the vertical component of the velocity is 0, but the horizontal component is still 4.07 meters per second. The speed at the high point is then 4.07 meters per second. Using conservation of energy, we have EKI plus EGI equals EKF plus EGF. Then rearrange this formula, we have EGI minus EGF equals EKF minus EKI, which gives us negative delta EG equals delta EK. Use this equation to solve for the change in height. We have negative mg delta y equals 1/2 m times vf squared minus vi squared. Then we know delta y is given by vi squared minus vf squared over 2g, which gives us approximately 1.1 meters. So we can make the final statement for question A. The bullfrog reaches a maximum height of 1.1 meters above the ground. Okay, have a look at the solution here. Do you have any questions? All right, if no questions, let's have a look at question B. Okay, so the change in gravitational potential energy is delta Eg equals mg delta y, right? And we know all the values here. So delta Eg is 3.6 joules. As in part A, the horizontal speed of the bullfrog does not change. So the only change to its kinetic energy comes from a change in its vertical speed, which we have delta Ek is 1/2 times m times Vxf squared plus Vyf squared minus 1/2 of m times the sum of Vxx squared plus Vyi squared. And simplify this equation gives us delta Ek equals 1/2 times m times Vyf squared minus Vyi squared. The initial vertical speed is Vyi is Vi sine theta, which equals approximately 4.68 meters per second. And now use conservation of energy theory. We have delta Ek equals negative delta Eg. and this gives us 1/2 times m times vyf squared equals 1/2 times mvyi squared minus delta Eg. So multiply both sides of the equation by 2, we have, and divide both sides by m, we have vyf squared equals vyi squared minus 2 delta Eg over m. And then put all the values in, we have vyf is approximately 2.4 meters per second. So the bullfrog speed at height of 0.82 meters is 2.4 meters per second. Okay, any questions? All right, then let's have a look at a concept called isolated and open systems. All right, in previous contents, we have learned about the conservation of mechanical energy, right? Mechanical energy includes both gravitational potential energy and kinetic energy. However, the conservation of energy includes other forms of energy, such as thermal, elastic, electrical, chemical, light, and sound, and so on. To understand transformations between these forms of energy, it's important to know the distinction between an isolated and an open system. First, an isolated system is a system that cannot interact with any other system or exchange energy with its surroundings. An object in an isolated system might exchange energy with other objects within the system, but energy never moves into or out of the system. The parts of the system are isolated from any influences outside the system. In reality, the universe itself is the only completely isolated system, but you can define a system that has minor influence from its surroundings as an isolated system. For example, you might consider a diver to be an isolated system if you ignore influences such as air friction and the energy of vibrations in the diving board. An open system, on the other hand, is a system that can interact with another thermal system, with another external system. An open system can exchange energy with its surroundings. In reality, a diver is an open system that exchanges energy with the air, the diving board, the water, and other real-world systems. Physicists sometimes refer to an isolated system as a closed system to contrast it with an open system. But be careful with the differences between the three terms: open system, closed system, and isolated system, which are illustrated in this figure here. Many systems analyzed in this lesson can be modeled as an isolated system. The concepts of isolated and open systems allow us to state the law of conservation of energy more formally. So according to the law of conservation of energy, we have the following formal statement. Energy is neither created nor destroyed in an isolated system. It can only change form. Okay, any questions? All right, then next, let's have a look at biological energy transformation. It's difficult to imagine a second of a day without observing some type of energy transformation. Each time you turn on a light, walk to class, or listen to your favorite song, energy changes from one form to another. Energy conservation involves transformations between many types of energy. Many biologically important energy transformations involve chemical energy. Biochemical energy is energy stored in the cells of organisms and is used to perform all life processes. Green plants produce biochemical energy during photosynthesis. Every time you blink your eyes, raise your arm, or move muscles, you transform biochemical energy stored in your body to mechanical energy that enables you to move. Biochemical energy can also change to forms other than mechanical energy. The bioluminescent jellyfish in figure 6 shown here uses the transformation of biochemical energy to light energy as a defense mechanism against predators. Electric eels transform biochemical energy to electrical energy to stun their prey. During intense exercise, the change of biochemical energy to thermal energy in your body causes you to feel warm. In each of these transformations, total energy is conserved. All right, next, let's have a look at another important concept, which is called power. So we have learned that the hydroelectric stations generate millions of kilowatts of power. The term power and kilowatt are probably familiar to you already, right? But what do they actually mean? Time enters into work energy ideas through the concept of power, which relates the rate of change in energy of a system over time. A man using a rope to lift a crate does work on the crate as it moves from the floor to a height h, as shown here in figure 7. The displacement changes the potential energy of the crate by an amount mg delta y. This energy comes from the man as he pulls on the other end of the rope and does a amount of work w, which equals mg delta y on the rope. If this work is expended during a time t, then the power P exerted by the man is defined as P equals W over T. So intuitively speaking, the power is actually the work done in a unit time, right? The SI unit of power is watt, named after James Watt, a developer of the steam engine. 1 watt is equal to 1 joules per second. Note that the symbol for watt is not italicized, but the variable used for work is an italic W. Careful with the difference here. Notice that power is a rate at which work is done. Work is a way to transfer energy from one system to another over time. As a result, power is also equal to the energy output of a device per unit time. In addition to mechanical energy, you can consider how other types of energy, including chemical energy and electrical energy, are involved in conservation of energy situations. The concept of power also applies to chemical and electrical processes and devices. There is a power output or input associated with many of the electrical devices in your home. For example, a typical compact fluorescent lamp is rated at 23 watts or 23 joules per second. This rating means the lamp consumes 23 joules of electrical energy for every second it is turned on. Likewise, electric devices such as computers and DVD players also have a power rating. So here, table 1 lists the power output and consumption of a number of common devices. So the distinction between power consumption and power output is important. For example, a fluorescent lamp consumes a certain amount of electrical energy for which you pay the utility company, right? And it outputs a certain amount of energy in the form of visible light, along with a certain amount of thermal energy. The following tutorial illustrates the definition of power as change in energy over time. So let's have a look at a sample problem here. A car accelerates from rest to a speed of 27.8 meters per second in 7.7 seconds. The mass of the car is 1.1 times 10 raised to the power of 3 kilograms. If ignoring friction, can you determine how much power the car requires? Okay, I'll give you 5 minutes to consider this question by yourself, and then we'll have a look at the solution together. All right, have you finished? Okay, let's have a look at the solution together. So we can use the power equation, P equals WT over T, right? And use a work energy theorem to relate W to the change in kinetic energy delta EK. The work done on the car equals its change in kinetic energy. The car starts from rest, so the change in kinetic energy equals a final kinetic energy. W equals delta EK, which is EKF, the kinetic energy in the final state, which is 1/2 times mVF squared, which is approximately 4.251 times 10 raised to the power of 5 joules. Therefore, P equals W over T, which is 4.251 times 10 raised to the power 5 over 7.7 seconds, which is approximately 5.5 times 10 raised to the power 4 watts. So the car requires 55 kilowatts of power. Okay, have a look at this solution here. Do you have any questions? Okay, please remember to complete your homework on Google Classroom and submit them before the deadline, okay?